But just for those of you who don't know me, I'm Bill Hansen. In 2017, I was in exactly pretty much the same boat that all of you were, not knowing very much about rocketry other than the pointy end goes up and the flamey end goes down. My background is as an Air Force pilot and strategic planner, among other things. So even though I had, fairly good aerospace background, I certainly didn't know much of anything about rockets and especially high-powered rockets. And so now that I'm in the seat, I wanted to try to spin people up early on so that those of us who didn't have that deep background in high-powered rocketry like some of the old heads do could get up on the step, just press on from there. So why are we here? We're here to just basically spin you up on the basics of rocketry. And so that's what we'll be doing for the next hour or thereabouts. What's next is what I'm calling Rocketry 501, the graduate course. And this is going to focus on the difference between the rockets we're going to be talking about in this class, which are basically just the basic hobby rockets, and what you're going to see for the Cup. And then we're also going to spend time talking about the scoring procedures and the scoring rubrics. And so that's going to be, those sessions are going to be ones that all the judges will have to go through to, and this will give everybody hopefully a common sight picture that we can take forward and make our scoring and judging tasks a lot easier. Okay, so the basic parts of the rocket. We've got, here's my high-tech graphics here. You've got the nose cone, we've got the airframe, which is the part everything fits into. It's got fins, the green thing's a motor that sits into it, and then it's got a parachute. And, a lot of these things are very, very simple deals. When we get to the 501 course and look at the Cup rockets, those are obviously much more complex. But if you understand how these things work, then this will help you understand the Cup rockets a lot better. Okay. So basic aerodynamic forces, the engine, the motor provides thrust to push the thing forward. Acting against that thrust is the forces of drag. Either due to the parasitic drag from the airframe structure or drag due to the aerodynamic forces acting on the structure. So gravity obviously plays a role, and then the fins and the rocket body itself produce lift. And so all four of those forces tend to work together to determine where that rocket flies, and hopefully we want it to be able to fly nice and straight. So here's what a typical rocket flight looks like for a hobby kind of rocket. That kind of black vertical thing, that's a launch rail. And the rocket basically is attached to the launch rail by little plastic buttons. And that rail guides that rocket. Once the motor ignites, then the rocket accelerates up the rail until the point where it exits the rail. And the rocket now is flying under, under its own power, and hopefully has enough speed on it so that the control surfaces can keep it going straight. And so the rocket will continue to accelerate until it hits the motor burnout, which is its max velocity. At that point, it's simply coasting upward, where the forces of drag and gravity are slowing that down until it reaches its maximum point, or what we call the apogee. And at that point, the parachute deploys, and then it drifts down at a fairly slow rate of speed until it lands, hopefully in some place where you can find it and bring it back. So that's really a fairly simple thing. So let's talk about terminology. The one word you're going to hear over and over again is caliber. And basically the caliber, just like the caliber of the bullet, is the diameter of the airframe. So if the airframe pretty common airframe is 4 inches. And so 4 inches is 1 caliber. And you'll see that a lot of measurements, a lot of rules of thumb are based on calibers. And so you'll hear more about this than you ever wanted to know. But so caliber is something to keep in mind. And then you've got basically two things. One is the center of gravity. And that's if you could imagine yourself putting your finger underneath the rocket and finding that point where that rocket balances. That's the center of gravity. So half the weight on one side and half the weight on the other side. The other thing we're going to see is what we call the center of lift, and sometimes it's called the center of pressure. And that's basically the point at which where the center of all the aerodynamic forces acting on that rocket come together. And so you'll see that because you've got fins that stick out, that the center of lift is generally going to tend to be close to where the fins are. And and hopefully behind the center of gravity. And we're going to talk more about why that's important. And then the other important term that we're going to hear a lot about is what we call thrust to weight ratio. And that's what causes the rocket to accelerate, the amount of thrust over or divided by the rocket's weight. And so normally for cup rockets and most of the rocketry, high power rocketry associations, the minimum thrust to weight ratio is 5:1. And the reason why that's important is because if we go back to the previous slide, when the rocket clears that rail, it's got to be going fast enough so that the fins can keep it going straight. And so if it doesn't accelerate to a quick enough speed, then it's, who knows where this thing's going to go. So we want the thing to fly straight, and therefore we want to exit that rail at a fairly fast speed, basically over 50 feet per second. Okay. So stability, again, back to calibers, the amount of stability of a rocket is expressed as calibers of stability. So if we go back to our 4-inch airframe, 1 caliber is 4 inches. And if the center of gravity is 8 inches in front of the center of lift, then that's basically 2 calibers of stability. The key point here is that the center of gravity has to be in front of the center of lift. If the center of lift is in front of the center of gravity, then the rocket's not going to fly stable. And if the center of lift is way in front of or way behind the center of gravity, then that rocket's going to be overstable, and that causes its own problems. And so what we're looking for nominally for a cup rocket is somewhere between 2 and 6 calibers of stability at launch. Now, the stability is going to change during flight for a couple of reasons. First, it's going to change. Well, let me back up. First, it's going to change because the motor burns out. And so the motor burns out, that takes weight away from the back end of the rocket, and that's going to cause the center of gravity to move forward. Similarly, when the rocket is going very fast, close to the speed of sound, then the changes in the aerodynamic forces are going to change where the center of lift is, and that is also going to affect the stability. And we're going to talk more about that as we continue on. So why do we want to have the center of gravity in front of the center of lift? Well, the reason is, and if you just think about an arrow, if you throw an arrow with the feathers in the back, then it's going to tend to fly straight. But if you turn it around backwards and throw that arrow with the feathers going forward, then it's not going to fly straight. It's going to, as soon as it gets off a straight course, then it's going to deflect, and it's going to continue to do so. And so the same thing happens with a rocket. In this case, our rocket has the center of lift in front of the center of gravity. If a wind gust moves that nose over, then what's going to happen is that center of lift is going to continue to pull that rocket away from its intended direction, and it's going to go out of control. And that is a bad thing, because those big rocket goes out of control, who knows where it's going to land. So this is something that's going to be very important to you and that the team should, have this whale under control. But this is a good question to ask, when you're looking at a team is, okay, so tell me where your center of gravity and where your center of lift is. And that way you can get a good handle on just how stable that rocket's going to be. Now, obviously the other thing we want to avoid is to have the rocket being overstable. So if the center of gravity is way, way up in the front, so say this thing's like really nose heavy, and that what'll happen is that when you get a wind gust as the rocket's going upward, then that rocket's going to weathercock just like a weather vane, and it's going to turn into the wind. Now, normally we expect the rocket's going to be pushed downwind, but if it turns into the wind, then it's basically going the opposite direction of where you expect it to go. And for example, at the spaceport, we got, typical New Mexico winds out of the west. And so therefore, we expect the rocket to go east as the winds blow it. But if it's overstable, then it may go back to the west, which is where the team assembly areas and where the spectators will be. And so that's a bad thing. So we don't want the rocket to be overstable either. So, and then the other part is that if the center of gravity is very, very close to the center of lift, then that's what we call understable. And, as long as it's in front of the center of lift, it should return to straight flight, but it may not, just depending on, how much it gets deflected or perturbed. You just don't know what it's going to do. Likely it'll keep going straight, but there's also a relatively good chance that it won't. And so that's why we tend to have the teams keep their stability at between 2 and 6 calibers of stability. Okay. Any questions on that? That was a lot of data that I just threw at you, but this is a fairly important concept that that we'll return to again and again during the Cup.
So what is the impact of the fins?
Okay, so the fin basically basically establishes where the center of lift is. The larger the fins are, the more the center of lift is going to move backwards. And therefore, if you have real tiny fins, then the center of lift is going to be fairly far forward, because not only does the fins create aerodynamic forces, but so do the nose and the rocket body. Whereas if the fins are really big, then that's going to push the center of lift backwards, and it's going to tend to make the rocket more stable. So just like an arrow, if the feathers at the end of the arrow are nice and big, then that arrow is going to really track straight. It's not going to go very far, but it's going to track straight. So does that answer the question?
Yes.
Okay. All right, continuing right along. Like I talked about briefly, is that the center of gravity is going to move forward as the motor burns. And so you may have something that starts out at 2 calibers of stability, but because the motor burns up all its fuel as the rocket's accelerating, then that's going to cause the center of gravity to move forward. And you'll normally see it about 2 to 3 calibers of stability farther forward at burnout than it is at launch. And like I said, the center lift is going to change during transonic and supersonic flight, but I'm going to hold that detailed discussion until we get to the advanced course. Okay, so we kind of talked about just the general, what happens during the rocket flight, but I want to break this down a little bit and talk about, what happens at the pad, how we go about launching it, the parachute deployment, and then recovering that, because these are all things that the teams are going to have to perform. And actually, as part of the Cup requirements, we have the teams create checklists for all of these things. And so this is something that you should at least be familiar with, because you're going to ask the teams to show you their checklist. And that way you can make sure that they're actually covering the kinds of things that they're supposed to take care of. Because, these rockets, they're big, they're heavy, they're full of rocket fuel, they may have black powder in them. So these are not, benign objects. And so safety in this and doing things in the right way is very, very important. And so we very, very much stress this with the teams. And in fact, if you see unsafe practices, then you should step in and stop the team from whatever they're doing, or go or get somebody who's more experienced to ring in on this, or and you also have the opportunity to either reward teams for exceptional safety practices, or you can penalize teams for being unsafe or for violating the rules. And this is something that you'll be wanting to pay attention to. Okay, so when they get out to the pad, a lot of this stuff is going to be taken care of. Most of you will not be going downrange with the teams, so this will all occur out of your sight, but we want to make sure that you've got a good situational awareness. Obviously we got flames coming out of the back, so we don't want any flammable materials. That's not a problem out at the spaceport, but if you're ever at a hobby launch somewhere, then that's something to pay attention to. Okay, we get the rocket up on the rail or launch tower, and that can be quite an involved process. Some of these rockets weigh upwards of 100 pounds. They're, some may be 20 feet tall. And so it's not, you're not just, walking out there with one guy standing the rocket up and going. You may need several people with a ladder and other things like that to get that rocket mounted on the rail. And then all the Spaceport Cup rockets have electronics. And so once the rocket's on the rail, pointed upward in a safe direction, then the teams will arm the electronics, and then they'll connect up the motor igniters. And then the rocket is at that point ready to launch. Okay, once again, just going back to the site. So once you hit the ignition, then the rocket's going to accelerate up the rail and up until burnout, apogee, and recovery. So once the rocket's up on the thing, everyone withdraws to a safe distance. And for the Cup, it's going to be 1,500 feet because these are big motors. They'll give a countdown, and then they'll do the motor ignition from the launch control facility. So that'll all be remote control. And then the rocket's going to accelerate up the rail. And as I said, it's got to be flying fast enough to maintain stable flight. So at a minimum 50 feet per second. For the Cup rockets, we'd like to see 100 feet per second. Okay, how tall is the launch rail? Good question. The launch rail at the Cup is 17 feet. So they got 17 feet to get up there to make sure that in order to get that rocket all the way up to speed. Good question. Yeah, a lot of places, if clubs and stuff like that, the launch rail will be a good deal shorter. Usually 8 feet is what you normally see if you were going to launch from Alamogordo or one of those places like that. But because the Cup rockets are big and heavy, then they need more, essentially a bigger runway to do that. Yeah, they do have specific rules as far as being up on the ladder, and I can get into those with detail, but it's in the rules and requirements document. It's all spelled out in both there and in the range standard operating procedures, both of which are available at the ESRA website, and I'll put up a link to that for everyone to look at. Okay, so once the rocket
Hey, Will, sorry, Shirley. You mentioned
go for it.
The 100 feet per second, but you didn't finish that sentence. So what did you mean with that? You said the minimal one is 50 feet per second, but then there was something about 100.
Oh, 100 feet per second is what we like to see.
Oh.
So yeah, so basically, if the rocket is going, if their simulations show that the rocket's going at least 100 feet per second off the end of the rail, then we consider that, that's a good rate of speed, and the rocket's pretty much assured that it's going to fly straight from that point. If it's between 50 and 100 feet per second, then we make the teams do some detailed simulations under a variety of conditions to make sure that the rocket is going to fly straight no matter which way the wind's blowing or how fast the wind's blowing, and so forth. So that, and then if they can show that via simulation that, if they're only coming off the rail at 75 feet per second, then that's good. But anything below 100 feet, they have to show via simulation or via flight test that the rocket is in fact going to be stable. Good question.
Understood.
So at the predetermined altitude, which for a hobby rocket is going to be somewhere close to apogee, then the rocket is going to separate using either black powder charges or compressed or CO2, compressed CO2, or similar mechanisms such as a spring or a piston to split the rocket into two pieces and then allow the parachute to deploy. And so for hobby rockets, what they have is that the motor itself has an ejection charge that goes off after a certain amount of delay. And so that's what they call motor injection. So in other words, the rocket will go, and then, say the delay timing is 8 seconds, then 8 seconds after motor burnout, then that ejection charge is going to go. And at that point, the rocket's going to separate. Cup rockets are going to use electronics, and are in fact are going to use what they call dual deployment, where you deploy a drogue chute at the top of the trajectory, and then the larger chute later on. And the purpose of that is just so the rocket doesn't go 6 miles downrange into the New Mexico wind under the parachute. If you think about a rocket, some of these rockets are going to 30,000 feet. If you put out the parachute at 30,000 feet, then you're going to see fairly stiff winds up there, and that rocket may end up over in White Sands, which we don't want to have happen. And so what happens is we pop a small chute that basically gets the rocket falling straight down at a controllable rate of speed, and then when it's close to the ground, then it puts out the large chute, and that's just a lot easier recovery. And we don't have, and that'll keep us from having teams out on the range trying to find their rockets when they've drifted huge distances, which they sometimes can do. So recovery, again, we're just waiting for the rocket to land. One of the big rules is you do not try to catch a rocket, even if it's falling underneath the parachute. You stay clear from that thing. Keep an eye on it, and then once it's on the ground, then as I said, these things have black powder charges in them usually, or electronics. So you want to make sure that those charges have actually fired, and that the electronics are disarmed so that you don't get any nasty surprises when you pick that thing up. The one big change from this year's Cup is that all the rockets are required to have GPS trackers on them. And Da Vinci is bringing in a big van with some real fancy antennas and everything like that. And they're going to be tracking all the rockets in the air and on the ground in real time. So that when the teams recover the rocket, go to recover, we'll be able to tell them exactly where it is, so within a fairly close range. And we think, based on the 2019 Cup, the teams that had GPS, we weren't usually recovered their rocket in about a half an hour. Teams that did not have the GPS usually took 3 and 4 hours to do so. And so for safety reasons and to move people, get the launches done quickly, we don't want to have people wandering around the desert for several hours. So this year, everybody's got a GPS on board their rocket, and hopefully that will make things go very, very smoothly when they go out to recover them. So other needed parts, we talked about the nose, the airframe, the tail fins, and the motor. You've got to have the little plastic rail buttons that hold the rocket on the launch rail. Those are that's a thing that we'll talk about this more with the 501 class. But if you think about that, those rail buttons are the only thing that hold that rocket on the rail. And so if you got a 100-pound rocket, then those rail buttons need to be on there pretty good. And so one of the things that a lot of judges do is they'll make the team pick up the rocket by the rail buttons just to make sure those things will hold on. You got to have something to hold the motor on. Usually that's a plate with a big screw fitting on the back of it, which is really important because if that motor leaves the rocket, then that motor is going to go flying, somewhere, and we may not like where it lands. And then they have the shock cord, which is how the rocket and the parachute are attached together. Typically, that's going to be either 3 times the length of the rocket. So if the rocket's 10 feet long, that means the shock cord's going to be, 30 feet long, and the parachute's going to be attached to about 10 feet from one end and leaving the other piece. And the reason we do that instead of having it at the in the midpoint, I mean, if you think about it, the rocket's in 2 pieces. If you have the parachute at the middle of that shock cord, then those 2 pieces of the rocket are going to sit there and just bang together all the way down to the ground. Whereas if you have one at 10 feet and one at 20 feet, then they're much less likely to hit each other. Then we talked about parachute deployment charge. For most of the Cup, vast majority, they're either going to use black powder charges or CO2 cylinders, and then of course the motor. And we got 3 kinds of motors that we're going to see in the Cup: solid, liquids, and hybrids. And so let's talk about the motors. So a motor in hobby rockets or high-powered rockets are going to be classified by letter. And so each letter is basically twice as powerful as the letter before that. So a B rocket motor is twice as powerful as an A, C is twice as powerful as a B, and so on. And so when you get to an H class of motor, that is the point at which we call this high power. And in order to fly an H class or larger motor, then you have to be nationally certified, or this has to be your Flight 2 certified in order to use that kind of motors. So, these are, there's a lot of energy in these things. And so that's one of the reasons why we regulate this so closely. Most of the Cup rockets you see are going to be either class L through class O. Most of them, of the vast majority, are going to be M class for the 10,000 feet rockets, and most of the 30,000 rockets are going to be O class. And of course, the other thing, besides more thrust, the bigger the motor, the more it costs. And so, like a small M motor is going to cost somewhere around $500-600, whereas one of these huge O motors, you're talking a couple thousand. So teams are going to try to buy the cheapest motor they can that'll do the job for them, because like all starving students, they're short of money. And so, like I said, M's and O's are the motors you're going to see the most, but you will see a few L's and you will see some N's. Okay, so solid motors, the most common, and we're going to talk about those in detail. Hybrid motors, we're also going to talk about this in some detail. The liquids are something that is only done at the Spaceport America Cup. It's not a normal hobby rocket kind of thing. So I'm going to defer that discussion till the 501 course. So how do we record? How do we figure out what a motor is? So it's basically, here's the secret decoder ring. So you got 3 elements. The first one's the letter, and that tells us what the total impulse or the total power of that rocket is. And so an M motor is going to have somewhere between 5120 and 10240 Newton seconds of impulse in there. And so those are pretty strong motors. My last M-class motor went to almost 15,000 feet and broke the speed of sound. So those are pretty hefty motors, and they will get the thing going. And so, okay, so here's the quick quiz. So if every letter is either doubled or half, what's the impulse range for an N motor? So that's
10,000 to 20,000.
yeah, basically 10,000 to 20,000, and an L motor is going to be basically 2,500 to 5,000. So you can see that there's, the one letter makes a pretty big jump, I should say, into in terms of total power. And then the second number is going to be the average thrust of that motor. So the M1315 is going to have 15 newtons of thrust. And so for those of us who high school or college physics was or mechanical engineering was a long time ago, a newton is the amount of power needed, amount of thrust needed to accelerate 1 kilogram by 1 meter per second squared acceleration. So you can see that those are going to that's going to give a lot of acceleration. And then the final thing after the dash, it's either going to be the time delay if it's a number, or P meaning plug means there's no motor ejection, and then you have to do it electronically. And so you're not going to see any motor ejection rockets in the Cup, but this is again just for just so that you have the basics here.
So this is the same kind of numbering system that the little Estes hobby rockets use, right?
Right, exactly.
Oh, wow.
So you'll see an A or a half A or a B or C or D.
Right.
So yeah, the little Estes rockets are basically using the same thing. And so a C motor is twice as strong as a B, so like an Estes would be like a C3-4.
Right.
Meaning, that to C motor, it's got to have 3 newtons of thrust, and it's got to have a 4-second delay. So that's exactly how they work. For commercial and military solid rocket motors, which is ammonium perchlorate, or APCP for short. So that's the most common material you make out of motors. But there you will also see what they call research motors, or for the Cup, student research and development motors that will have a variety of custom formulations to try to get more impulse out of the same size of a motor. And then interestingly enough, you can make motors out of sugar. And there's a whole bunch of alchemy about how you make sugar motors. But basically, if you ever tried to the thing in high school chemistry where the teacher got a bunch of sugar and lit it on fire, well, it's the same thing. Sugar will burn, and therefore you can make a motor out of sugar. And there's real specific ways to do that. And I'm not going to get into the nuts and bolts of that, but just so that these are the 3 kinds of solid rocket motors that you're going to see for the Cup. So here's the cutaway of a typical motor. On the left-hand side, there's the red thing's a cap that goes over the nozzle. And then these kind of light blue things in the middle, they're what they call propellant grains. And so the pieces of the ammonium perchlorate, say, are going to be cast into grains that are, say, an inch or 2 long. And then those grains are going to be basically stacked together inside the case. And notice that the grains are hollow. And so what happens is that motor essentially burns from the inside out. And that hollow space in the middle is the motor's combustion chamber. And so what they'll do is they'll take a igniter, they'll push that igniter clear up to the top of the motor. And so then when you fire that igniter, that will set the very, very top of that motor on, start that motor to burn. And then as that motor burns, it'll be, it'll push the exhaust back down through that tube, through the nozzle. And that's what creates the thrust for the model. And interestingly enough, most motors you have basically just a circular hole in them. But if you do different kinds of holes that change the amount of surface area in that hole, then the thrust characteristics of the motor will be somewhat different. And so people, especially those who do their own motor construction for the research motors, will actually use a variety of different internal geometry to try to get the motor to burn exactly the way they want it to. But so you're not going to really need to see anything about this, but just so that you know, when the teams are talking about grains of propellant, those are those basically cast cylinders of the ammonium perchlorate or sugar or whatever they're making the rocket motor out of, and that those are stacked together inside of that an aluminum case, and then that's what makes the rocket go. So these are fairly there's no moving parts whatsoever in this thing, and it just goes on its own. Okay, a step up in complexity is what we call a hybrid motor, and this is something you will also see in the hobby rocketry. So basically what you're doing is that the fuel grain, rather than being ammonium perchlorate, is usually something, butyl rubber or some kind of a plastic. And then what you do is you push nitrous oxide through there. If any of you guys were hot rod enthusiasts or anything like that, people use nitrous injection to make the motors go faster. Same thing with a rocket motor. You can push the oxidizer, which is the nitrous oxide, through that fuel grain. You have an igniter that puts basically a spark plug that puts it in there, and then the nitrous oxide gives the oxygen, the fuel grain gives the fuel, and then that thing burns, and then out the end of the nozzle it goes. And so these are obviously more complex, although they're actually fairly simple beasts. And because of the fact you got to have a tank on the end, they're usually quite a bit longer than a solid motor is. And so that's one of the trade-offs you get. You get more power, but then you end up having to deal with a bigger motor. So that's a hybrid in a nutshell. Again, you're not going to be, when we get to the judging, you're not going to be asked to spec out these people's hybrid motors, because we do have folks who are really, really smart in those things that go over that before you get to the teams. But this way, at least you'll know when the teams say, "Oh yeah, we got a hybrid motor," and then you can nod wisely and go on from there about your judging. So we've got, one of the things you're going to be looking at is how the rocket's constructed, because that's part of the scoring, is basically how good of a job the teams do in building their rocket. And so we're going to talk about some rules of thumb and a few things that you're going to be looking for. So we'll get right into it. So the construction rules of thumb, again, here we are back to calibers. So a typical rocket is going to have between a 10 and a 20 aspect ratio, meaning that the length of the rocket is going to be between 10 and 20 times the diameter of the rocket. So, for example, a 4-inch rocket could be, anywhere from 40 inches to 80 inches long. So 6 feet 8 inches is usually a pretty is pretty much what how big these rockets will be. You will see that teams are using in some cases up to 8-inch airframes, and so you can imagine if it's an 8-inch airframe and 20-to-1, then those are pretty long, pretty big rockets. The aspect, this kind of, like I said, it's kind of a rule of thumb, general guidance, not an exact science, but teams that stick within those rules of thumbs will generally have safe rockets that will fly as expected. The fin size, again, general guidance. You want the span is how far that fin sticks out. And so you want that fin to stick out at least 1 caliber. And that the at the root, the base where it attaches to the airframe, you normally want that to be 2 calibers. Now, I will say again, general guidance, and these numbers are basically for what they call the basic 3 fins and a nose cone rocket. If you have a rocket with 4 fins, then obviously if you have more fins, you don't need the fins to be quite as large. And so you'll see smaller fins on those teams that choose to have 4 fins versus 3. But like I talked about briefly earlier on, by and large, you want to have fin that's big enough to give you the right kind of stability you want, but you don't want it to be too big, because if it's too big, then that fin creates more drag and the rocket's not going to fly as well. So that's so construction rules of thumb, those are just things. And if you see something that's much different from that, then that's a good question to ask the team. Say, hey, I see your fins are only 0.75 calibers. Tell us why you did that. And that way you can figure out if the team is actually paying attention. Okay, venting. This is some of these rockets are going up to 30,000 feet. And so if you think about it, if you have a balloon that you put air in at sea level, and then you let that balloon go up in the atmosphere, then as the atmospheric pressure decreases, that balloon's going to get bigger and bigger and bigger. Well, the same thing happens with the inside of a rocket, is that the rocket obviously doesn't expand like a balloon, but if you've got a big enough difference between the pressure inside the rocket and the pressure outside the rocket, then you can break that airframe. And again, that's not a good thing. And so normally, actually it's a requirement that each bay that's basically sealed off has to have a vent hole in there to keep the rocket from breaking at altitude. And then for cup rockets with electronics, they've got an altimeter in them, so you need to read accurate barometric pressure. And so you normally have to have several vent holes in the electronics bay to let that outside air pressure get to the altimeter in the electronics. So those are, again, those are things to look for. These are, this is pretty basic stuff, but you'd be surprised every once in a while you'll catch somebody who you ask them where the vent is and they're like, what? And so those are, again, another thing to pay attention for. Talked a lot about fins already. The fins are the most likely failure point. And you can think of it, if you think about that rocket's going fairly fast. Several of these rockets are going to go well above the sound barrier. And so there's a lot, there's a lot of aerodynamic stress on that rocket and on that fin. And therefore that is basically the weakest point. And so there's basically 2 ways to attach a fin. Either what they call a surface mount, where the fin is just basically glued onto the outside of the airframe, or through the wall mount, where the fin actually goes into the airframe and attaches to the outside of the motor mount. And so you can probably see, fairly intuitively that a through the wall fin is going to be much stronger than a surface mount fin. But why would you do a surface mount fin anyway, than if a through the wall is stronger? One of the things that you will see is that some of the teams are doing what they call a minimum diameter rocket. And so a minimum diameter rocket is basically one where the size of the motor is the same size or maybe just a hair smaller than the airframe. And so if the motor is basically fitting tight inside the airframe, then there's really nothing for it to attach to. And so you have to attach it to the outside. And so, with some of the teams, you will see surface mount, but that's because of the size of their motor. If the motor's too big, then they can't do through the wall. One thing that all teams will do is they'll do what they call fillets, which are just, if you see the middle graphic going up and down, those are just like little little reinforcements that go between the fin and the rocket airframe. And that serves two purposes. One, obviously, it makes it stronger, makes the attachment stronger, gives more surface for the adhesive to attach to. And it also gives you better aerodynamics, less drag. If anywhere there's a sharp corner, even if the on an airframe, like a sharp angle between the fin and the airframe, then that's going to create more drag than if you have a smooth attachment. The other thing that you will see teams do quite a bit is what they call a tip-to-tip layup. And that's basically you got your fins, and then you're adding a layer of fiberglass or carbon fiber that goes across the tops of the fins in the airframe. And then that basically locks it all in as one, complete, one solid unit. And so you'll see a lot of the teams have their fin mounts, and then they'll have several layers of carbon fiber over the top of that to keep those fins nice and stiff. Kind of as a rule of thumb, if when you're looking at a rocket with a team, just wiggle on that fin a little bit and see if it should not wiggle. And so that's something that pay a lot of attention to. Some of these teams are going to be working on their rockets, up until the last moment, and so you'll see, fins that quite aren't all the way there, as well as far as solid attachments, and so that's something that you're going to want to pay attention to. Attachments for the parachute and the shock board. When that rocket's up at altitude, you got two things that's working on it. The first is that you've got the ejection charge. It's the black powder, the CO2 canister that's basically pushing that rocket apart, and it may push the rocket apart fairly briskly. The other thing that's happening is that even though ideally you want that the rocket to separate at apogee, where it's basically stopped going up and it's not going sideways, a lot of times it doesn't hit it exactly. And so the rocket may be traveling at a a fairly good rate of speed when that thing separates. And so you're going to, you can get, somewhere close to 50 G's of stress on that shock cord, depending on how violent the opening is. And that will, and so, that part of the rocket where all those things attached together has to be really, really strong. And so usually you're going to have steel forged eye bolts or U-bolts that are going to attach that, and you're going to have stuff that's rated 2,000 3,000 pounds of braking strength. So you want to have fairly stiff hardware for that. The other thing that you sometimes see is that these things are epoxied or glued inside the airframe in some way. Again, you want to make sure that that thing is not going to go anywhere. And if you got questions, then this is where, and again, another chance to ask the team. It doesn't look as strong as it is maybe it needs to be. Tell me about how you tested this to make sure that this is in fact strong enough for what you intend to do. And so those are so again, other things to pay attention to. Okay, safety. So these last few slides are going to be just about safety. Again, min safe distance from launch. These things have got, the ammonium perchlorate is not an explosive, it burns, but it can, if something happens and it overpressurizes that rocket, it'll throw pieces a long way. And so for cup rockets, we're going to be more than 1,500 feet away from that rocket when it goes. And so that's a minimum safe distance. Like I said on the pad, these things are, full of rocket fuel. They've got black powder, they got electronics, they got everything there. The key thing is that they want to have as few people possible on the pad as you need. Obviously, if you're getting up a big heavy rocket, you're going to need some muscle to do that. But some teams will try to have their whole team go out there, 20 people, and they don't all need to be there. So if somebody doesn't have a role to play out on the launch pad, then they shouldn't be there. Again, make sure there's no flammable material. Make sure everything is safe until the rocket's on the rail pointed upwards. Never point the rocket at people. And, think of it as a gun. You don't want to point the nose or the tail at people, just in case. The team should be wearing safety glasses or face shields. The teams, along with the people who are supervising on the pad, are going to check to make sure that the circuit isn't hot, because if that wire is hot when they connect the igniters, that motor is going to go right now. And if there's somebody standing next to that, that's going to ruin their whole day. And so those igniters need to be safed, shunted together with leads touching, so there's no static electricity possibilities until that point where they're inserted in the motor and they're hooked up, and then the rocket's ready to go. Once that happens, you back away and and launch. Again, recovery, safe recovery, very important. You got to maintain visual. Be careful about approaching the rocket. Again, there may be unfired charges, there may be electronics may still be hot. So don't just run right up to it and pick the thing up. Sometimes the rockets will fall into trees or power lines. If that happens, or in the case of the Cup, there's no power lines out there, but if it goes over in the white sands, then the team can't go get it. You don't want to go to a dangerous place or, a place where you're not allowed to be. And so if that happens, just stay clear, and then we'll figure out how to get the rocket later on. Again, they want to make sure everything's been fired, everything's safe, pointed away from people, and then you can pick up the rocket and come home. Questions thrown a lot at you. Have all the Cup rockets flown previously, or will some be making their first attempt? Some teams, this is their first year at the Cup. Most of the rockets, especially the US and the Canadian, Australian teams, they will have test fired their rockets before they bring them to the Cup. And so, so most of those rockets will have been done already. The international teams, it's a more complicated thing, because if you think about it, you've got rocket fuel, you may have black powder. Some of the countries where these teams come from, they don't let people have those things, and they don't have airspace or the opportunity to launch. And so, for example, for the Indian teams, the first time that they launch that rocket is going to be at the Cup. And so, that's something we've been paying very close attention to. All the teams now have to have both domestic and international have to have a mentor and a certified flyer of record that supervises the construction, makes sure that rocket's as good as it possibly can be before it gets here. But yeah, you're going to see some Cup rockets that's the first time they fired it, just because of the limitations from their home countries.
What percentage of the rockets launched are successful?
Pretty much, it'll be interesting this year since we haven't flown in 2 years. But normally, 75% of the rockets are going to reach their altitude. Probably only 10% will fail in some spectacular fashion, and we're hoping to drive that level down. But by and large, the rockets will in fact launch successfully, and will make their reasonably close to their assigned altitudes. We have a lot of safety inspections going on. Again, like I said, the teams have to have a mentor that they work with, And then they also go through both a safety inspection when they first get out to the cup of their rocket to make sure everything's going as it should be. And then they're also going to get another inspection right before they take their rocket out to the pad. And so, we'll have looked at these things several times. Hopefully we catch all the obvious and most of the not so obvious problems, and the rockets will do well. But every once in a while, Murphy just steps in. I was mentor for the New Mexico State team. Their first year they competed, and they had their rocket motor casing fail, which is extremely rare, never happens, something totally out of their control. But instead of burning out the end, the fuel started to burn out the side and caused their rocket to break up pretty spectacularly in doing so. Okay, where are teams storing their rockets before they go to the launch pad? The teams have a specific area where they will have assigned work areas where they'll be. They have that areas arranged now so that there's plenty of space between them. And as far as danger of inadvertent firing, the rockets won't be completely put together until they're ready to go out. And what I mean here is that they're not going to put the motor is going to be one of the last things they put in there, and then they'll put the black powder charges in, and if they use that, and they will get the electronics so that they're ready to be armed. But those black powder charges will be safed. There's no igniter for the motor. The electronics will have power, but they will not be armed and active. And so and none of those things are going to happen until that rocket physically gets out to the pad. And so there's obviously if you're dealing with black powder and stuff like that, there's always a certain degree of chance that thing's going to go. But we try to keep that under pretty tight control to make sure that that they're not doing anything in their areas that they're not supposed to do, and that everything that makes the rocket hazardous is only going to occur when they're on their way out to the pad, and not just normal. Yeah, but some of these teams, especially the East Coast teams, if they, the first year I was a judge, we had 3 kids from a little tiny liberal arts college in New Jersey that schlepped their rocket clear across the country on the back, strapped to the back of a Volkswagen Bug, and and they still managed to get out and fly. So you'll see. So it'll be quite interesting. Where it gets more interesting for the transport issues is obviously for the international teams. Just because the airlines don't like to carry stuff or whatever. So, and no one's going to let you walk on the airliner with a bunch of black powder in your bag. So that all that stuff has to get shipped separately. So that's that can be a fairly significant challenge. And in fact, most of the international teams, at least the ones that like India or Egypt or some of those countries where they can't get commercial motors, they will actually, we have vendors on site that those teams have been in contact. And so they're not even going to have their motor until they get out to the cup. Same thing for black powder. A lot of that stuff, they're having to locally source that because they can't get it in their countries. And so again, if we, it'll be under the control of someone else up until the point where they get out there and get ready to launch their rocket.
Yeah, one question. So there's a safety team or so. So you before you mentioned okay. The question is, what's the interaction between us as judges and those people? So I assume there's other people which really assess the safety, or let's say the go ahead for the rockets to launch. So,
Right.
so
Okay. Yeah. Great question. So, we're kind of keeping, obviously everybody's, concerned with safety. And that's why I'm giving you some of this stuff up front. So you'll at least be sensitive to the kind of things that can be unsafe. And, you're going to have a lot more contact with the teams than the safety reviewers. The safety reviewers are going to do their thing. When the teams check in, we're going to safety review their rocket right there at the convention center. Again, before the teams go out to the pads, they're going to get another safety inspection. But your interaction with those safety folks is that, if you see anything, and I mean anything, that raises a question in your mind, or you want, a better read on, then the safety guys will have a different kind of badge that says safety on it. That'll be a different color than the regular judge's badge. And so, we hunt those folks down, or hunt me down, because I'm a safety reviewer as well. And and then get someone to take a look at it, and to work with the teams to make sure that it's okay. Because it can be, there's all sorts of little tiny things that that may not necessarily be in the books or in the rules documents, but and we try to cover all the bases. But every once in a while, you run into something completely new. The teams are dreaming up brand new things to do, and and they can be quite creative in finding ways to do things that no one ever thought about before. And so if you see something that even raises a question in your mind, then grab a hold of one of those safety guys, or one of the launch ops guys, or one of the ESRA staff, and get a read on it. But it's not your job to do the safety inspections for them, but safety is pretty much everybody's job out there. And so that's how the relationship is.
Okay, understood. Thank you.
Okay.